By the way, this is something dear to your hearts here in the state of Washington. Of course, Eastern Washington. How many have been into Eastern Washington and seen some of these features of the Lake Missoula flood? Many of you had. How many have never heard of the Lake Missoula flood? Yeah, there's several of you. When I go to a lot of other places, 95% of the hands will raise when I ask that question. Hardly anyone's ever heard of it. And I'm trying to educate people on it. And the National Park Service is doing this, and other private groups. They want to have a national flood path, national monument, or something like that. I'm not quite sure the status of it. Some of you might know more about it than me, but they're trying to emphasize this with kiosks here and there along the paths from Montana through Idaho, Washington, Oregon, and Idaho. Anyway, what does it teach us? Well, let's tell the story of the Lake Missoula flood. A man named J. Harlan Bretz, you can see the plaque at Dry Falls. How many have been to Dry Falls? Oh, yeah, not surprised. By the way, his first name is the letter J. That's it. When I've written articles on the Lake Missoula flood, I'll use his name, J. Harlan Bretz, and the editors come back to me and say, you need a dot in there. And I said, no, he didn't have a dot. His name was J, okay? J. Harlan Bretz. Anyway, J. Harlan Bretz started out as a science teacher at Franklin High School in Seattle, Washington. And he was getting his degrees in geology, I think partly from the University of Washington and later on from the University of Chicago. I'm not quite sure of that. But he was looking at the new geological maps coming out from Eastern Washington one day, and he noticed some really strange features in Eastern Washington. He noticed a drainage pattern with suddenly a vertical wall at Dry Falls, and about 300 feet with these deep plunge pools, what he determined plunge pools. He said, you know, when a drainage occurs, it erodes the rock. And if you have a waterfall, it erases it after a while. So you should have a gradual descent downward. You should have no waterfalls. So that was really strange. And not only that, it's dry. So what gives? Well, I might add for you fishermen, it's really great trout fishing in this plunge pool here. Every time I'm there, there's someone down there fishing. Anyway, so he postulated a monstrous flood could only explain this, and the flood ended and left these dry falls, sort of like that. Then he looked at another location just up from the Columbia River in the Quincy Basin, the edge of the Quincy Basin. He noticed similar features to Dry Falls. These are called the ancient lakes, and with the green algae in the summer and the black basalt, which is about 300-foot cliffs, it's a real stark contrast to water eroding over the ridge and forming this plunge pool. It started near the Columbia River and backed up about 2 miles. And there's several other plunge pools that are not filled with water towards the Columbia River. And he noticed this a little further south along that same ridge. It's called, I think, Babcock Ridge, if my memory serves me right, along the western Quincy Basin, southwest Ephrata. You have you can't hardly see that in the light, but anyway, it's a 300-foot deep canyon. The Columbia River's down here, and there was a waterfall that backed up and eroded the basalt into a 300-foot canyon, and there's no lakes in there right now. Then he noticed all these gravel bars in places that are really dry, like this place at Malden, southwest of Spokane. There's my wife for scale. You can see the flow of water coming from the northeast to the southwest. And here's another gravel bar. This gravel bar, this has formed delta structures from the erosion and deposition. And this gravel bar is located on a ridge south of Arlington, Oregon. So the water overtopped that ridge and eroded the ridge and formed a delta on it. And then you have all these other bars around the area. This one is about, this is near the Bonita Bridge, 40 miles northeast of Yakima. Can you see that well? That seems kind of washed out. Anyway, here's the Saddle Mountains. It's a lava ridge of Columbia River basalt that's buckled up in a ridge. And here is the Columbia River up here. And here's a 100-foot bar of gravel that's 15 miles long sitting out there. Anyway, there's gravel bars all over. This one is on the Snake River. It's about 200 feet high, and it's a basalt gravel bar. Anyway, there are probably 100 or 200 gravel bars out here, and some of them are so large that to form a gravel bar, the water has to be deeper than the gravel. So this implied water hundreds of feet deep that are moving through here. And this is a huge gravel bar. It's about 200 square miles. It's called the Portland Delta, where part of the city of Portland is built on, and Vancouver. It's about 300 feet deep of gravel, 200 square miles, and the Columbia River is cut through the middle of it like this right in here. And then you have all these erratic boulders spread all over the place. An erratic boulder is a type of rock that does not outcrop in the local area but has been transported somehow. Here is a granite erratic boulder found near Highway 14 in the Columbia Gorge. It's pretty large. And here's another granite boulder. This one has a lot of weathering on it and lichen, and so it's a brownish color. It's probably the largest granite boulder I've ever seen, and this is on a ridge south of Arlington, Washington, you know, where the water overtopped the ridge. And these were carried by icebergs, by the way. That's the only way you can get them down here. They didn't roll down. And then in the Willamette Valley, a plot of all the erratic boulders that don't outcrop in the area was made quite a long time ago. Every one of these dots clear down in Eugene, Oregon, were plotted, hundreds of them. You know, they don't outcrop in that area. And here is a famous erratic boulder. Has anyone ever seen this one 50 miles southwest of Portland, Oregon? Okay. Well, maybe one of you. There's a sign by the road saying glacial erratic on your way out from McMinnville. This is a special erratic boulder. I can't see it very well, but it's a shale that's been heated up and metamorphosed called an Argillite. This is a typical rock that you find in western Montana. This type of rock does not outcrop anywhere in the state of Oregon. And it's very angular, and since it's like a shale, if it rolled down, it would break up. Then J. Harlan Brett saw the silt that covers the basalt in eastern Washington has been eroded in areas, and it's formed streamlined hills about 100 feet tall in the direction of flow, a kind of a lens-shaped stream-like hill like you see here near Palouse Falls, where the water was coming like this and streamlined it to a dimension of 3 long versus 1 wide, 3-to-1 ratio. And then many canyons were cut by the floodwaters. For instance, Grand Coulee, vertical-walled, flat-bottom canyon called coulees. That's why they call it, this is the Grand Coulee. It's 900 feet deep and about 25 miles long. That's the upper Grand Coulee, separated by dry falls. And then the lower Grand Coulee is about 25 miles long. And that is this one right here looking down, and it's filled with lakes all through here. How many been to those lakes recreating? Banks Lake, some of the other ones, can't think of them anyway. And then the water came through the Columbia Gorge and widened the Columbia Gorge and made it more vertical so that you have the nice waterfalls of like Willamette Falls and so forth. Anyway, J. Harlan Brett pointed these things out, and he did the research year after year, started publishing it in the standard secular literature starting in 1923 and ending in 1932. He published several dozen papers, and they were accepted. But it had a huge problem. It implied a flood that they couldn't imagine a flood like this because they had rejected anything of significant size. And here's a kind of a summary statement. The establishment, that is the geologists and professors, as represented by the United States Geological Survey, closed ranks in opposition. Instead of testing Bretz's theory or flood on its own merits, they rejected it on general principles. Well, why did they reject it on general principles? They rejected it because it was too large, and some have said too biblical in proportion. And it's because they've accepted slow processes of erosion and deposition over millions of years, and they didn't believe in catastrophes. And that's why they rejected it on general principles, not on evidence. There's hundreds of pieces of evidence out there in eastern Washington, and they rejected it because it was too biblical. Now, Bretz kind of caused some of his own problems in that he admitted freely, I don't know where the water came from. Maybe it was some flood from British Columbia that came underneath the ice or something of that sort. So he didn't know where the source of the water is. But a man named Pardee actually knew but kept quiet to save his skin and his reputation. He did research in western Montana. And in western Montana is a series of deep mountain valleys. And along that you see these parallel lines that ended up being shorelines. Here is one over the city of Missoula. Can you see this distinctly? Is there any way to turn those lights down a little bit? Oh, if not, I'll describe them. I'm sorry for being kind of picky, but if you can't see what I'm showing you, it kind of doesn't help. Anyway, you can see some of the lines there. Oh, I'll point over there. Okay. On Mount Jumbo, on the other side of the University of Montana at Missoula, here's the shorelines right here. I've been up here, and they have an average spacing of about 35 feet vertically. They're very even, and you can hardly see them when you are walking on them because they're just little tiny rolls. And there's about 40 of them there. So there's a question of, first of all, how they originate, but it at least implies shorelines from a lake. And you see these all over the area. This doesn't show up very well, but this is in the northern Bison Range. I'm going to skip that because it doesn't show up well. Anyway, when you all add it all up, like I said, there's dozens of locations all through western Montana showing shorelines. You end up with a massive lake right in here, glacial Lake Missoula. And it was 2,000 feet deep right there at the ice dam at the Montana-Idaho border. At the city of Missoula, which is right there, is 1,000 feet deep, and it backwashed up the Bitterroot River and up this way on I-90, which is now I-90. And it was blocked by the ice sheet that filled up Flathead Lake in the north. It was formed by a finger of the ice that had blocked the ice in northern Idaho. The ice was about 2,500 feet deep. We know that because the tops of the mountains were unglaciated around it, so it filled up the valley. Just sort of like you see a lot of glaciers in Alaska that fill up valleys. It was a valley glacier. So that's glacial Lake Missoula. About 540 cubic miles of water, I think about 4 times the volume of Lake Erie. So that's a huge amount of water, and it was blocked by ice. That's kind of an unstable situation, isn't it? Because ice floats. Anyway, you know what happened. It burst through. It destroyed the ice dam, and it emptied glacial Lake Missoula in 2 days. And it spread through your state here. Well, first going through northern Idaho. And it carved up the 100 feet of silt on top of basalt. It eroded 50 cubic miles of basalt and silt down through here. and it raced down to the Columbia Gorge and backed up at Wallula Gap there and formed a lake, an instant lake 800 feet deep. They give the name Lake Lewis, and it lasted 5 days, and it backwashed water up the Walla Walla and the Yakima Valley and up the Snake River clear past Lewiston, Idaho into Hell's Canyon. And then the water came and formed another lake around Hermiston, and I think there might even be another one here, but then it flowed through the Columbia Gorge 1,000 feet deep. Well, I might add that when it went over Spokane, Washington, it was 600 feet deep. No wonder the geologists rejected it. For over 40 years they rejected it. And then it backwashed up the Willamette Valley, clear to Eugene. It moved over Portland, Oregon, 400 feet deep. And then it rode it out here, and it carved a channel a little deeper, a little submarine canyon out on the continental shelf. So that's the story of the Lake Missoula flood. And you see the evidence all over the place now. And from the air, you especially see it, like here at Camas Prairie in northwest of Missoula, Montana. How many been to Camas Prairie? Just a couple of you. Well, this is an area northwest of Missoula where the water, there's a little Bitterroot Valley here, they call it. And here's a ridge right here, and then here's a slope going down this way. And the water was about 800 feet deep right here, and as Lake Missoula emptied suddenly, catastrophically, going 80 miles an hour through what's called Eddy's Narrow, which is a very narrow area of the Clark Fork River Valley. It was moving about 60 miles an hour over this ridge, and it formed these ripple marks, gravel ripple marks, 3 stories high of gravel. Now, Pardee knew about this, but like I said, he didn't say anything. He kept quiet, and the issue wasn't resolved until the 1960s. And since we have aerial photos, we see ripple marks on a lot of gravel bars, over 100 of them, like this one right here, and this one right here. Now, this one was taken from road level, so it doesn't show up as well as this one, which is an aerial photo. Also, the erosion eroded a lot of basalt and carried basalt boulders for miles, like this one right here, southeast of Ephrata. This is part of a huge gravel bar, about 200 square miles, maybe about, I'd say it probably averages about 60 feet deep. And on it you see these huge boulders. Some of them are granite that come from the Grand Coulee area. And this is basalt right here. And it spread these things like gravel on a stream bottom. And from the air, we can see the path when it eroded the light-colored silt and left exposed the black basalt. You can see the paths of the Lake Missoula flood down like this right in here. There all kinds of minor channels like this, but a major channel, the Palouse-Cheney Scabland track and the Grand Coulee track down through there. And that is Wallula Gap, where the water could not exit through there. It was probably a lot more narrow at one time, and the flood widened it. And so that's what caused the 800-foot deep lake around Pasco, Washington. Let's see. Now, when it backwashed up the Walla Walla and Yakima valleys, it sent these, it formed these layers, just like sedimentary layers. And like this is at Bering Canyon in the Walla Walla Valley. This canyon is in the stack of Lake Missoula flood. We call them rhythmites. Rhythmite is rhythmic sedimentation. In this case, it's generally sand and silt, rhythmites. And they're about 6 feet thick at the bottom, and they thin going up. I'm going to make a point on that later. And so this was cut by accident. This material is so soft that this canyon was cut in 6 days by the overflow of the irrigation canal that runs the top of the ridge. See, there was a big windstorm, and it added all these tumbleweeds into the irrigation ditch. They thought they're going to cause a flood of the field, so they bled it out on a side ditch into this part of a field, and it formed that canyon about 100 feet deep in 6 days. That's how soft that material is. But scientists have discovered an ash layer near the top. Now, this ash is said to be from an eruption of Mount St. Helens, which erupts every 125 years on the average. And this ash, you can see about the 11th rhythmite from the top, and it's very distinct. You can see it in the Yakima River Valley, and you can see it in the Walla Walla River Valley. So, even though J. Harlan Bretz invented one Lake Missoula flood, Richard Waite comes along in the 1980s and said, well, what's the odds of Mount St. Helens going off at the same time we're having one Lake Missoula flood? He said, that is too improbable. So what went on here? Well, I think what happened is that each layer that you see there represents a single Lake Missoula flood, and that after the flood you have the top of it exposed, and the ash from Mount St. Helens eventually goes off. It's exposed 40 or 50 years, and then it accumulates on it. And then you have another flood that puts the next rhythmite on top of that, and so on. So he believed each rhythmites, and there's about 40 of them in this area, he believed each was a separate flood. So that started the multiple Lake Missoula flood idea. Separated, each one's a separate flood, and in between you had to wait for glacial Lake Missoula to fill up, the ice dam to form and fill up again, and then it breaks again and again, at least 40 times. But actually there's more to it. From a place north of Grand Coulee in the Sandpoil Valley, a man did a PhD thesis. He drilled down in that valley, and he found 96 rhythmites of a different sort, different than the ones you saw in this Burlingame Canyon. These were pretty thick rhythmic sedimentation. And he said, well, I think glacial Lake Missoula had 96 floods at the peak of the last ice age. And they believe in multiple ice ages, by the way, 50 in the last 2.6 million years of time. But just after the last, he thinks, well, let's round it off to 100. So now they think that there's about 100 ice ages. But there's lots of problems with this idea, of which I will just quickly mention some. First of all, a man did a PhD thesis, I think his last name is Lister, on sediments north of Missoula and south of Flathead Lake, and he found out that the sediments, bottom sediments of glacial Lake Missoula indicate only one filling of glacial Lake Missoula, because if it filled and emptied, you'd see all these erosional patterns in there, but no, it's too even to have been filled up more than once. So he says there was only one filling of glacial Lake Missoula. Also, a group from the University of Alberta in Edmonton, 8 geologists came out here to re-examine it and published an article in the journal called Geology in 1999, headed by John Shaw, and they said, we see only evidence of one flood, and that evidence in the Sandpoil Valley, where that guy claims there was 96 rhythmites or 96 floods of Lake Missoula, there's a major problem with it. Where they did the coring was only about 6 miles from the Columbia River basalts that cover the lava that covers eastern Washington below the silt. So if there was separate floods of Lake Missoula coming over the basalt, and it would move up the Sandpoil Valley, it would drop all this basalt cobbles and gravel and basalt sand. But he said there's no basalt in those rhythmites. So those rhythmites can't be from floods of glacial Lake Missoula at all. You know, a pretty obvious problem. And why did the guy miss it? You know, this commonly happens in geology, I find. There's a lot of things they miss out there. And a lot of times they miss them because they got their uniformitarian glasses on and they only see slow processes over millions of years, and they miss some key elements out there. Well, how did those rhythmites form? Well, you know, the edge of the ice sheet in northern Washington was just to the north of this location, so it probably those were drainage representing 1 year of deposition. You know, they were pretty thick, about this thick. 1 year of deposition over about 96 years of melting in that area. I think that's what they're from. They're actually drainage rhythmites caused by each year of drainage. Also, when you look at the rhythmites closely, which I will do here pretty soon, you find there's no erosion in those rhythmites. Did you see how even they were? Let's go back to see how even they are. You know, if we had a flood and it laid down a layer like this, then the next flood come, how fast do you think that flood would be moving? It'd be probably moving 30 miles an hour at the start. Do you think it's going to not erode or not form a little valley here or there? No, it's going to tear that thing apart. We should have a mishmash in here if each one of these was a separate flood. Also, the rhythmites thin upward. I mentioned that. They thinned about, maybe 8 inches. So that's exactly what you'd expect in one flood, where the worst part is at the start, and the most sediments are at the start, and each layer represents a pulse, moving up these valleys, pulse, pulse, pulse. And this is what Brett's thought. This is what a guy who analyzed this in the 70s, Victor Baker, believed in one flood. He thought they were pulses. And why would you have pulses? Because the path of the flood was 100 miles wide, but there were areas that, where it was converging and diverging. So when you have converging water and diverging water, the level of the water goes up in convergence and down in divergence. This causes a wave. When you pile it up, it causes a wave, and that causes it to speed up and form a pulse going up the valley. So it makes a lot of sense from a hydrological point of view that each of these rhythmites is a pulse. Also, you find 20 rhythmites in front of Wallula Gap. Remember, Wallula Gap is the area where the water's heading for and trying to get through. It's moving 30 miles an hour or more into that area. And yet, right in front of Wallula Gap, you have 20 rhythmites that don't show erosion at all. Each flood should wipe out any rhythmites there, that were there from the previous flood. You see, these are things I found some of these on my own from researching, but other geologists had pointed these things out. Also, something called Clastic Dikes, which now these are these 20 rhythmites near Wallula Gap. Now these are weathered. If you could form a slice down it like Burlingame Canyon, they'd be pretty even. It's because you have a slope wash and weathering. But in that sequence here and all through these rhythmites, you find what's called Clastic Dikes. These are these dikes of material. They're the same material as these rhythmites going up through there. And they go from the bottom to the top. If each of these rhythmites was one flood, these are dewatering structures because it was wet sediments, and as you squeeze it, and it's got maybe 600 feet of water on top of it, and as the water drains, the pressure releases and the water wants to come out, you see. That's how you could explain them, but from one flood. If each rhythmite was from separate floods, the Clastic Dikes would only be the vertical distance of one rhythmite and stop. Then you'd form another set for the next rhythmite. You see, the texture of that sequence is totally different if each was a flood. So there's lots of evidence against this idea. So I'm going to shift gears. There was only one Lake Missoula flood. There might have been some smaller ones afterwards if the ice dam in northern Idaho, rebuilt, but they'd be smaller. There's possibly a few minor ones after one large one. That's what the evidence says, and even some secular geologists have concluded that. But I want to change gears and say, well, this is all great stuff. We love looking at that stuff, but what does it mean to us? What do we learn about the flood, from the Genesis flood, from looking at this? Well, we learn that the Lake Missoula flood eroded 50 cubic miles of material in a matter of days out of eastern Washington, hard basalt and soft silt. That's a lot of erosion from one little tiny flood. and it deposited the material up to 100 feet thick or 125 feet thick in those valleys that backwashed up, showing rapid deposition. Multiply glacial Lake Missoula by 1,000 times, maybe 5,000, 10,000 times, then you have the scale of the Genesis flood, and we can get an idea how you can rapidly erode the pre-flood world and redeposit it as thick sedimentary rocks in some areas. And by the way, in some areas, the sedimentary rocks are very thick. On the continents, they average 1,600 meters, which, let's see, translated into feet is close to 6,000 feet. 6,000 feet average. Only 70% of the continents have sedimentary rock on them. So some are deep and some are shallow. Some are very deep. And of course, where you have igneous rocks, there's no sedimentary rocks. So we can account for it gives us an idea of rapid sedimentation. Also, when the Lake Missoula flood tore through the eastern Washington, it left erosional remnants. It didn't erode everything. It left erosional remnants. And we see erosional remnants on the surface of the earth today from the Genesis flood. I will show you some pictures soon. Also, it created what's called water and wind gaps. How many know what a water gap is? Okay, I'll explain. A water gap is essentially, it's a gorge perpendicular to a mountain range or a plateau in which water starts on one side of the mountain range and passes through the gorge to the other side. That's a water gap. A wind gap is where you have a V-notch on a ridge and no water can pass through it because it's a pass, and only wind moves through it. Anyway, a number of water and wind gaps were formed in the Lake Missoula flood, and we see thousands of these on the surface of the earth today that are big mysteries to uniformitarian secular geology. Also, we have an analog or an example of how we can rapidly deposit continental shelf material and subsequently form submarine canyons through that shelf material. So this is just a summary of what I'm going to talk about coming up here. So let's talk about, first of all, not only sheet deposition, but also you had huge currents moving fast over the surface of the earth during the flood, forming planation surfaces. Planation surfaces are on all the continents. 60% of Africa is one large planation surface that is bulged up or down. This is a planation surface around Grand Canyon. Notice how flat it is. And in this area of Grand Canyon, 10,000 feet of sedimentary rocks used to be on top of here and were eroded off and from currents moving towards the east and northeast. We know that from some of the gravel left behind, and the shape of the gravel shows you the current direction. Anyway, formed a generally flat surface in the Grand Canyon area. And then the Southern Rockies came up out of the floodwaters. The currents going east, they backed up going to the west, and they channelized, carving Grand Canyon rapidly. So we see that of the Lake Missoula flood, where you see some of the basalt has been plain flat, but then it's been carved up into buttes and coulees to form the Channeled Scablands, and sometimes some deep troughs, like southwest of Spokane, Washington. You see some of these deep channelized erosion, like Rock Lake, Sprague Lake along I-90. But you look out in the distance from that rest area near Sprague Lake, you can see that the evenness of the basalt. It's been roughened since, but you can see kind of less like a planation surface that has since been dissected and eroded. This is a common pattern we see on the surface of the earth all over the world. And this pattern fits with the runoff of the floodwaters off the continents. Erosional remnants. This is the erosion of a field in South Africa caused by a flash flood. Notice the erosional remnants left behind. See, floods don't erode the whole thing. It leaves a few erosional remnants, showing that there was a flood and not millions of years of erosion. When we look in the upper Grand Coulee, we notice it looks like the walls of the coulee right there, but actually that is Steamboat Rock. That's an erosional remnant where when Grand Coulee was eroding rapidly, it, for some reason, didn't erode that rock there. It's 900 feet tall, erosional remnant, carved by the lake. Well, it didn't carve it, it missed it for some reason. We don't know why, because we weren't there. And of course, this is looking from the top of it. It's a nice 900-foot hike up to the top. And we're looking down south towards the lower coulee that was eroded in a matter of days. Rapid erosion. Multiply that by a couple thousand times, you get an idea of the erosion during the flood. And it's kind of interesting that this is a glacial erratic on top of that Steamboat Rock. And I think Grand Coulee was formed because the edge of the ice sheet was right there, and when the water came from the east, it hit the edge of the ice sheet and came down parallel to it, carving Grand Coulee. That's how I think Grand Coulee probably got started. Once it got started, it funneled the water through there, eroding it rapidly. But you know, we see erosional remnants like this by the thousands over the earth, just sticking up out of nowhere, like Devil's Tower, 1,200 feet tall. It's the throat of a volcano. The volcano was probably erupting right up in here in the air. Now, these conduits of volcanic material moving up don't move up in air. They have to be, sedimentary rocks have to be around here to form this. So implying rapid erosion that somehow left Devil's Tower. Now, Devil's Tower is like basalt. It's got columns, and because of freeze-thaw weathering, it's going to erode quickly. Devil's Tower, which is claimed to be millions of years old, sticking up there millions of years, can't last that long because of freeze-thaw weathering. It should be a pile of rubble in a matter of 10,000, 20,000 years, implying that something rapid eroded all that sedimentary rock around there, probably several thousand feet of sedimentary rock in northeast Wyoming. How many been to Devil's Tower National Monument? Yeah, a number of you. Anyway, when you go to national parks, look at some of the kiosks there and see, does that make sense? Because, and a lot in how old they say this is 10 million years old, 20, 30, it varies. The ages varied over the years. I got kiosks saying different dates. The width of Devil's Tower has not changed much in those millions of years. Now, that really doesn't make sense. It should have, that the width shouldn't change in millions of years. That makes no sense from an erosional point of view. And we have lots of other erosional remnants all over the earth, thousands of them. Like this one right here, we had massive erosion during the flood. We can show in some places that you've had over 10,000 feet of erosion, like I just showed you over the Grand Canyon area, eroding that whole area down to a flat surface or nearly flat surface. Anyway, here's a little massive erosion occurring down like that and ending up with that, Monument Valley. Monument Valley are erosional remnants from the runoff of the floodwaters. And then water and wind gaps were formed. Now here is a map. Here's the Snake River right here. And here's Washtutna Coulee. The Palouse River, before the Lake Missoula flood, would run this way through Washtutna Coulee into the Columbia River. And here's a ridge of basalt and silt that is about 500 feet higher than Washtutna Coulee and the Snake River. During the Lake Missoula flood, the waters came down from the north and overtopped that ridge, forming, first of all, an 8-mile wide canyon right in here that narrowed to a narrow canyon right in here. And then over here, we had another canyon formed called Devil's Canyon. Now, after the Lake Missoula flood, the Palouse River, instead of continuing its old path, takes a left-hand turn and goes through Palouse Canyon into the Snake River, forming a water gap. Also, Devil's Canyon is a wind gap. First of all, here's Palouse Canyon. How many have been to Palouse Falls State Park? Yeah, okay. More of you should go out there. You can, gives you an idea of the powerful erosion mechanism. But anyway, here is Palouse Canyon. It's a water gap where the Palouse River now runs through it from Washtutna Coulee to the Snake River. And here's Devil's Coulee, the one I showed you on the map. You can't see it. Anyway, to make a long story short, you can hardly see it cut through the 500 feet, but it's blocked here. So no water can pass through it, but only wind, so it's a wind gap. And hopefully you can see, oh yeah, there we go. You can drive up to it and down into it, and here it is. This is where it's blocked, where no water can pass through here. And as you go down there, you can see it's a total of 500 feet deep, narrow canyon, wind gap formed during the Lake Missoula flood. But we have these water and wind gaps by the thousands all over the earth, similar to what the Lake Missoula flood did, meaning large floods create these features, and we have them on the surface of the earth that they have serious trouble trying to explain. Water and wind gaps. Now this is one near where I live. This is near Cody, Wyoming. I'm looking west towards Yellowstone Park. These are the Rattlesnake Mountains, and they're 2,500 foot deep here. The Shoshone River starts in Yellowstone Park and moves east. It could have gone around this ridge here, like this, and out into the Bighorn Basin, but instead ends up going through this gorge, 2,500 foot deep, as if the river cut the gorge. It'd have to run uphill and then down. And they have all kinds of exotic ideas on trying to explain this, but none of them can be proved, and a lot of them don't make any sense. And when you drive through the water gap, there's the gap there. I'm looking east now. This is Buffalo Bill Reservoir, filling up this valley. Here's the low spot where when the sediments were higher, say a million years ago, assuming their time scale, the water should have went out here. But why did it go through here? They don't know. This is one of thousands of pieces of evidence. The Appalachian Mountains alone have 1,700 water gaps going through ridges when the river or stream could have gone easily around the ridge. These are common worldwide, and they can be produced easily by a major flood, as the Lake Missoula flood shows us. Here's another famous water gap. The Green River heads for the Uinta Mountains that are 14,000 feet tall. You know, when it hits the Uinta Mountains from the north, it is deflected a little bit to the east, and then suddenly it cuts through a slot canyon called the Gates of Lodore, a half a mile deep, right there. And it could have gone 3 miles further east and gone around a real low area of the Uinta Mountains to the south, where it ends up, but it cut right through the edge. Why did it do that? Well, they don't know. But during the flood, it can easily occur. Here's how we'd explain it during the flood. You have water moving perpendicular to a ridge. The ridge is probably moving up. There's some, low spots in the ridge. And a lot of times the water will funnel through those low spots, eroding them rapidly, like this right here, funneling it through as the tops of some of the ridges exposed. And it has to speed up because you have the same amount of water that was going over the ridge now has to go through two thin areas. So it has to speed up like water going from a wide pipe to a thin pipe. And as it speeds up, it catastrophically erodes these water gaps or gorges through mountains. And as it continues, the waters are draining. The water is funneling at high speed through these things, cutting these gorges until at the very end, we have a water gap, and this gave up too soon, and we end up too high. There's no water going through it, but only wind, so it's a wind gap. And here the river actually goes through the water gap. This is easily explained by the drainage of the floodwaters. And the Lake Missoula flood shows us an example of how they are formed, and we see these all over the earth, showing a global flood all over the earth from the surface features of the earth. We also have an analog of forming the continental shelf and the submarine canyons. Now, I can show probably an average of at least 500 meters of erosion on the continents as an average. When the continents were coming up out of the floodwaters, and the floodwaters were rushing off at high speeds into the deepening ocean basin, the eroded material is moving off at high speed. And it'll keep moving off until it slows down. And it's going to slow down when it hits deeper water. And that's the edge of the continents, forming the continental shelf, which are very mysterious features, some of them huge. And the Portland Delta is an example of how we can form a continental shelf easily. because it's a little bit different in principle, but you had water moving 80 miles an hour through the Columbia Gorge, and suddenly it widens out into the Portland, Vancouver area, and the velocity has to drop. And when the velocity drops, you have to drop your load, which in this case was gravel. So it's the same thing as the floodwaters are moving off the continents, eroding hundreds of feet of sedimentary rock and depositing along the continental shelf, forming the continental shelf rapidly. Then after the shelf forms, the currents narrow. You know, as the floodwaters drain, the currents go from wide currents, maybe 2,000 miles wide, to narrow currents, and they actually start eroding. And the Columbia River is an example of that. I don't think the Columbia River formed this. I think this formed, the delta formed first, and then the current came through here and sliced through there, and the Columbia River ends up going through there. This is the same way submarine canyons are formed. We have hundreds of submarine canyons. A lot of them are deeper than Grand Canyon, cut in the continental shelf. For instance, here's one of the largest continental shelves in the world, the Bering Sea Shell. This is the edge of the shelf right here. This thing is very shallow. It's about 400 miles long, all sedimentary rock deposited from runoff from the continent. But at the edge here, you have these big submarine canyons. This one right here, I think that's Zemchung Canyon, is twice as deep as Grand Canyon. It doesn't show up well there, but these are huge canyons, larger than Grand Canyon. The Bering Canyon right here is actually longer than Grand Canyon. So you have these submarine canyons cut by more channelized flow. Now here's a great canyon. This is a horrible picture. I took it with a flash, and you see what happens. Okay, but anyway, ignore that. Here's Monterey Bay. This is Monterey Canyon right here. That comes down like this. That's Monterey Submarine Canyon. It is as deep as Grand Canyon. And first the shelf formed. Here's the continental shelf right in here. And then after it's formed, you cut it in narrow channels rapidly. All this can happen rapidly from the drainage of the floodwaters. And the Lake Missoula flood gives us an example of how this can happen during the Genesis flood. So we have examples from the Lake Missoula flood of what occurred during the Genesis flood. And these features which I showed you, and I could show you more, are very difficult, if not impossible, to explain by the secular uniformitarian geologist. So in summary, what does it teach us? What does the Lake Missoula flood teach us? It teaches us that committed secular scientists will have great difficulty seeing evidence for Noah's flood, because despite hundreds of pieces of evidence out there, they rejected for 40 years, they rejected a flood. But it's interesting, most of them never bothered to go check it out for themselves. But one guy did. The most renowned glacial geologist, Richard Foster Flint, did go out to eastern Washington. And he came back with the report that normal rivers and runoff from melting glaciers can easily form all those features with slow processes over hundreds of thousands of years. That shows you the blindness that's going on. So I expect that secular scientists, because of those blinders, it affects your whole mind. They're not going to be able to see the evidence out there. I see it everywhere, evidence for the flood. And they can't see it anywhere. It's a psychological phenomenon that affects us all. Also, we learn more about catastrophic processes, because it's probably the second largest catastrophic flood. Oh, by the way, since the Lake Missoula flood, they have found other ice age floods around the earth. But Lake Missoula flood is probably one of the largest. We understand rapid erosion and deposition, and we also can understand from the Lake Missoula flood the enigmatic features found on the surface of the earth. Much of the surface of the earth has features that can't be explained, or even though they attempt it and have serious difficulty explaining these features, we can understand them from the Lake Missoula flood. So that's all I have, and I thank you for coming to this conference, and I hope you learned a lot.